I'm going to talk about scale-invariant online learning, and that's a joint work with my PhD student, Michał Kępka, and my collaborator, Manfred Warmuth. Okay, so that's a slide from one of the morning talks by Staszek Jastrzębski about stochastic gradient descent and the learning rate. And that's a quote from the book, a deep learning book, which says that the learning rate is perhaps the most important parameter, and you have time to tune only one hyperparameter, tune the learning rate. So the main point of this talk is to just get rid of the learning rate from the algorithm. Okay, so I'm going to start with introducing online learning. So online learning is a theoretical framework for analysis of algorithms. And here's one example of a typical online learning problem, the travel time estimation. So imagine that at every timestamp, there's a navigation software which needs to predict some travel time at a given road segment. Let's call it YT. And then given a feature vector, which let's say represents a correct traffic condition, so the vector of D features, the algorithm predicts with a linear model. So the prediction y hat is a dot product between feature vectors and some weight vector. And then the algorithm observes the actual outcome, the real travel time, and measures its prediction loss. And based on the prediction loss, which is here assumed to be a squared difference between the prediction and the true label, it adapts or updates the weight vector to predict better in the future. So another example would be online spam filtering. So at every timestamp, there's a spam filter which needs to classify an incoming email as either a spam email or a regular email. So now we have a binary classification problem with two possible labels, +1 and -1, and then given the feature vector xt, which let's say represents the email's body, the filter predicts with a linear model again. So the prediction is just a dot product between the weight vector and the feature vector. And the prediction y hat is compared with the actual feedback. Let's say there is a user which gives back a feedback, and then we can measure the prediction loss, for instance, using the so-called logistic loss, typically used in logistic regression, or it's also called cross-entropy loss. So the general protocol of online learning with linear models, which these two examples were special cases of, is as follows. So we have a sequential prediction problem such that at each trial, small t, from 1 to, let's say, some capital T, first, nature reveals some input instance xt, which is a d-dimensional feature vector. Then the learner or the algorithm predicts with a linear model and returns y hat t using some weight vector wt. And then the nature reveals the true label, and the learner suffers some loss, which is a function of the true label and the predicted label. And throughout this talk, we are going to assume that the loss function, it satisfies certain mathematical properties. Namely, it's a convex loss, otherwise it's really hard to show anything, and it has a bounded slope. So here are several losses which are often used in machine learning. For instance, 0-1 loss, squared loss, logistic loss. They are all plotted as a function of the prediction with a fixed label. So for example, squared loss and absolute loss are plotted with assuming that the true label is 0. The other losses are plotted assuming that the true label is +1 in binary classification. And for instance, in this talk, you can think of the loss function as, let's say, cross-entropy loss or logistic loss or hinge loss, which is being used in supervector machines, or for instance, absolute loss. But let's say not 0-1 loss, which doesn't have, which is not even differentiable, and clearly is not convex. Okay, so how do we evaluate the algorithm in the online learning? So first of all, in online learning, we do not make any stochastic assumptions on the incoming data sequence. So we do not assume that the data sequence which the algorithm observes is, say, IID. So how do we measure the performance of the algorithm? We just compute all losses the algorithm suffers and take the sum of those. So the total loss of the algorithm is just the sum of all losses incurred by the algorithm during the prediction process from time 1 to capital T. And then we want to compare the accumulated loss of the algorithm with the loss of some particular weight vector, let's say the optimal weight vector. Let's call it W star. It's like a target loss, right? Or the loss of the target weight vector which we would like to converge to. And let's call it the optimal loss. That's the total loss of a fixed weight vector. So here, the weight vector is changing all the time. Here, it's a fixed weight vector. And then we can measure the performance of the algorithm as a difference between these two. So this difference is called regret relative to W star, this, let's say, optimal weight vector. It's a difference between the loss of the algorithm and the loss of this optimal weight vector, and the regret quantifies some sort of suboptimality. So regret says, this is the excess cumulative loss for not having played with W star from the start. So how much more loss the algorithm has incurred by not playing with W star from the beginning. Of course, we cannot play with W star from the beginning, because if W star is truly the optimal weight vector, and by that I mean the weight vector which minimizes the cumulative loss on the whole data sequence, then W star is inaccessible until the very end, when we already know what the actual data sequence was. So we cannot compute it in advance. We can only try to follow it in a sense, and that's what most algorithms do. Okay, so what's the most typical approach in this setup to predict? Okay, sorry. I should have said that the loss of the algorithm is generally a quantity which scales linearly in t, because it's a sum of t losses. And similarly, unless we have no noise, which is very rare, the optimal loss is also a quantity which scales linearly in t, because it's also a sum. So in a sense, the difference between two can be trivially achieved to have also linear dependence on t. And then we say that learning is non-trivial if this difference is sublinear in t. So it grows slower than t. Okay, so the typical example and like most commonly used algorithm in this scenario is so-called online gradient descent, which is also called stochastic gradient descent in stochastic approximation setup. And it's a very simple algorithm which, given a new input instance, it essentially makes a small step along the negative gradient of the loss at the current data point, where eta denotes the step size or so-called learning rate. What's this nabla t? Nabla t is just the gradient of the loss on the current data point with respect to the weight vector. And we essentially take the previous weight vector and subtract the gradient multiplied by eta. And now this algorithm can easily be analyzed, and it can be shown that the regret of this algorithm, so the difference between the cumulative loss of this algorithm and the cumulative loss of the weight vector W star, can be tightly upper bounded by the following quantity, which is a squared norm of the optimal weight vector divided by the learning rate plus learning rate times the sum of squared gradients encountered during the prediction process. This assumes that we start at 0. So from one point of view, there is this influence of initial conditions, which scales inversely with the learning rate. So if we have large learning rate, we quickly forget that we started from 0. And here is another term which scales with the learning rate. So if we have large learning rate, this term might be large. And now we want to optimize this quantity, so have a bound on the regret which is optimal. And in this case, we can essentially choose learning rate which minimizes the right-hand side. So what's the minimum? So it's pretty simple. We have essentially we need to find the minimizer of the following quantity, some constant a over eta plus b times eta. Taking derivative gives us the optimal learning rate, which is square root of the first term over the second term. So in particular, we can tune the learning rate optimally by choosing the learning rate which is proportional, which is equal to the ratio of the norm of the weight vector, optimal weight vector divided by square root of the sum of the squared gradients. Unfortunately, it's impossible to do that because we don't know what W star is, and we don't know what kind of gradients are we going to see. So what people working in theory do, okay, so if we choose this learning rate optimally using this expression, then we can actually plug into the definition of the regret, and we get this quantity, which is essentially W star, the norm of W star multiplied by square root of sum of squared gradients. And as I said, this is impossible in practice to actually choose the learning rate this way, so what people in theory do is they say the following: we will constrain the optimal weight vector W star, as well as all W's played by the algorithm, to have norm bounded by some constant W, or belonging to some, let's say, set with diameter at most W, capital W. And we will also assume that we have a bound on the gradients, that they have a norm which is no more than, let's say, G, and both W and G are known to the algorithm. And then we can first upper bound all the gradient norms by G and the norm of W star by W, and then tune the learning rate on this upper bound in a very similar fashion. So we essentially choose eta star, which is equal to W, the upper bound on W star, divided by square root of, well, G squared is the upper bound of the squared norm of the gradient times T, because there are T gradients here. And then if we plug it into the regret bound, we get this quantity, which is essentially a quantity which grows only as square root of T, so sublinearly with T. And this is all nice, except that it's not really satisfactory, because we have bounds, right? And we don't really work with, we don't really tune based on the real data, we tune based on the upper bounds. So in fact, what works better practically is just to tune learning rate by trial and error. So to test various learning rates and choose the one which works best. Okay. So let's look again at stochastic gradient descent. So that's what already was shown on the previous slide. And then for linear models, this gradient has a very specific structure. So in linear models, the loss is the loss of the prediction, and the prediction is a dot product. So if we compute the gradient, we can use chain rule and first compute the derivative of the loss with respect to the prediction, and then compute the derivative of prediction with respect to the weight vector, and then we get the expression which is a product of two terms. One is a number, which is this derivative of the loss with respect to prediction, and the second part is just the feature vector. So essentially the gradient for linear models is proportional to feature vector. So for instance, for squared error loss, if we take a derivative of the squared loss with respect to the weight vector, we just first compute the derivative of the square, which is 2 times what was inside, and we multiply by the internal derivative. So this first quantity is just a number which I call GT. So essentially gradient for linear models is proportional to the feature vector. Okay, so now if we look at it more closely, and we can think of this problem in terms of physical units. So imagine that each feature has a physical unit, which I denote here in the square brackets as square xi. For instance, maybe euros or kilograms or meters or whatever. And let's assume that unit is different for each feature. Potentially it's the case. And let's even assume more that the label or prediction are unitless. It's just for simplicity, of course, they don't need to be, but let's assume that they are unitless, so they don't have a unit. Maybe the prediction has like probabilistic meaning. And in this case, if you look at what kind of unit should the weight vector have, it's going to be the opposite of the feature unit. Because if we compute the prediction as a sum of products, so for each term in the sum, the unit must disappear, right? To have a unitless quantity. So every weight should have a unit which is the inverse of the unit of the corresponding feature. But it's not the case here, because if you look at what's happening with stochastic gradient descent, then there is a mismatch of units. So units do not match because this term, GT is unitless because it's just the derivative of the loss with respect to prediction. Then we have a unit xi here. Here's the inverse, and here's the inverse. So, well, what kind of unit should the learning rate have? There's no single unit that learning rate could compensate. So it is also somewhat reflected in the regret bound. So it's just, let me just remind you, the regret bound, yes?
Sorry, why GT is unitless? It is derivative.
Yes, but it's derivative with respect to prediction, and we assume that the prediction is unitless. Those label and feature are, and prediction are unitless. So there are no units here, only here in the feature vector. Okay. So here is the regret bound after plugging in the optimal value of eta, and you can see that it actually depends on the norms of both W star and the gradients. So if we have various units of different size, this means that the first term here, W star, is going to be dominated by the largest inverse unit, in a sense, and the other one is going to be dominated by the largest unit. So this product can be really large. And the solution to that would be, well, units are mismatched unless we have a separate learning rate for each feature. And the learning rate is going to have a unit which is 1 over the square unit of the feature. And in this case, the learning rate will compensate units on each coordinate, but each feature must have its own private learning rate. Of course, this is impossible to tune in practice, even by trial and error, to have a separate learning rate for each feature. But let's continue with that. So if we have a separate learning rate per feature, we can essentially do the same analysis for online or stochastic gradient descent as we did with a single learning rate. And we get a bound which is of this form. So previously, the bound was like the product between the norm of W star and the square root of sum of squared norms. And here we have a bound which is a sum over all features of products, which is just the absolute value of the ith coordinate of W star multiplied by the square root of the sum of squared ith coordinates of the gradient. And the optimal tuning of the learning rate for each feature is essentially very similar to the optimal tuning of this single learning rate, except it only applies to a single ith coordinate. But it has a very similar form. And if you look at the actual expression, this is exactly what we want. So this learning rate has the right unit. So optimal tuning of the learning rate, optimal in hindsight tuning, which is impossible in practice, but still, given the math here, we can compute the optimal learning rate. It actually achieves this tuning, achieves this compensation of the units because it has the right unit. Because W has a unit 1 over xi, this has a unit xi squared, and square root is still xi, so in total it's 1 over xi squared. And then also in the regret bound, we see that units cancel because this has a unit inverse unit of feature. This has a unit, the unit as the features. So every term here is unitless. And the question in this talk is that can we get the optimal SGD bound with some adaptive tuning strategy, so without even tuning the learning rate? And the answer is yes, almost. Sure.
At the top, GT is equal to this difference, and why you divide over yt hat? I mean, why you divide by yt hat instead of divided by w?
It's just external derivative. So there should be a gradient here, and I compute the gradient in 2 steps. First, I take a derivative of the loss with respect to the prediction, that's GT, and I multiply it by internal derivative, which is derivative of prediction with respect to the weight vector. And that's essentially only xt, because the prediction is linear in the weight vector. So it's essentially a product of 2 parts, which corresponds to the chain rule of differentiation.
Okay. Thank you.
Okay, so there's a popular algorithm which is called ADAGRAD, which somehow tries to solve this issue of learning rate tuning to some extent. So it works like this. So it looks like stochastic gradient descent, except that in each step the learning rate is appropriately scaled, actually divided by the square root of the sum of the squared gradients. So it kind of looks similar to what we already seen in the SGD bound. But the problem is that still units are mismatched here. So even if you compute all the units, it suggests that the learning rate should have a unit which is inversely proportional to the unit of xi, which cannot be the case because we have a single learning rate for all features. And while learning rate still needs to compensate units, it cannot do so for all features at the same time. The same argument as for AdaGrad, it actually applies to two other similar to AdaGrad algorithms, so-called RMS prop and Adam. And actually, this phenomenon has already been observed previously, and it was heuristically solved in one of the algorithms which is sometimes being used for deep learning, which is called Ada Delta. Okay, so motivation here is that if we want to have a fully adaptive algorithm, which is going to get rid of the learning rate entirely, then the algorithm needs to resolve the scaling issue somehow. And that's where this scale invariance comes in. So what we can observe is that for linear models, if we rescale all the features, and it follows by inverse rescaling of the weight vector, then the prediction of the weight vector, and has losses and all the behavior of the algorithm, it remains invariant. So if we take a single feature and rescale all input data on that feature by some positive number AI, and multiply the weight vector by the inverse of this number, then the prediction after this transformation remains the same. So what does that mean? It means that, okay, so here's just a small reformulation of this by using matrices, right? So I just rewrote this, what was here, which is for every single coordinate by using a diagonal matrix. So I multiply the feature vector by a diagonal matrix, each feature vector by the same matrix, and the weight vector by the inverse of that matrix. So actually, here's A, and here's the inverse of A. And then the prediction remains the same, and this works for actually any invertible matrix, but here I'm only using diagonal matrices. So in particular, if we have an optimal weight vector, which optimal means like it minimizes the total loss on some sequence of data. So then if we transform this sequence of data by multiplying each feature vector by some matrix A, then if we take the inverse A times W star, it's going to be the optimal for the transform sequence. So this also shows how the weight vector transforms when we change the features. And this is natural because that's an optimal weight vector, so we would like the algorithm to actually undergo the same transformation. So we say that a learning algorithm is scale invariant if it returns the same predictions under arbitrary rescaling of the data. So no matter how we rescale the data, the algorithm is going to behave exactly the same, but not in terms of the weight vectors, but in terms of predictions and losses, because this is what is really important for the evaluation of the algorithm. So in particular, if we scale the feature vectors by a matrix A, then the weight vectors produced by the algorithm should rescale with the inverse of A, and then the prediction of the algorithm will remain the same. Okay, so here is one solution from 2013. It's so-called normalized adaptive gradient algorithm. This is an algorithm which actually is being used in kind of popular software called Wopal-Wabbit. And it's a default algorithm there. The algorithm still has a parameter, learning rate, and it keeps track of several data statistics. So essentially, this MT is like the maximum value at a given feature, which has been seen so far. Then we have S squared, which is the sum of squared gradients. So it's take a current sum of all past gradients squared. And then there's some kind of a weird quantity, which is the sum of normalized squared features. So it takes the sum of features squared divided by maximum value at that moment of time, at that particular features, and it accumulates this type of quantity. And the algorithm is defined this way, so that's a weight update. It looks like gradient descent, stochastic gradient descent, except that there is this whole thing here, and the reason for that is essentially to somehow make the scaling appropriate in terms of, let's say, units. And if we look at the units of all these quantities here, so it turns out that everything is fine as long as eta, the learning rate, is unitless, so we don't need to have units for eta. And then we can actually get the regret bound for this algorithm. The regret bound is of this form. The problem is that the regret bound, it scales properly. It scales this S is a square root of this thing, so it also scales a square root of the number of iterations in general. But this is achievable only under, again, optimal tuning of eta, which is unrealistic because optimal tuning requires to know this quantity here, which is the largest prediction by the optimal weight vector on any feature, which is inaccessible because W star is inaccessible in itself. So this also, the algorithm itself also has a crude scaling by the maximum. We don't like scaling by the maximum too much. We actually would prefer to have a scaling in terms of maybe some sort of a standard deviation rather than maximum or a sum of squares or something. And well, it achieves somewhat weaker bound than the optimal SGD, but most important thing is it still has a learning rate, which is to be tuned. And there's one more algorithm which is called scale-free mirror descent. It's kind of similar, so I'll just quickly go through this slide. So it also keeps track of several statistics, like again, maximum value at the given feature, negative cumulative gradient, so it takes all the gradients and accumulates the gradients, compute the sum with minus sign, and then sum of normalized squared gradients, the same quantity as on the previous slide. And the algorithm looks somewhat different. So instead of doing the weight update, it actually just calculates the weight vector directly without referring to the previous one by looking at the cumulative gradient rather than the actual gradient in a given moment. And then it scales appropriately by the squared max. And here is additional scaling by this normalized quantity. And if we look at units, it's again, everything is fine, except that there's still learning rate here, which needs to be tuned, and we have the same problem as before. So essentially, the regret bound is also somewhat similar to what was achieved by the algorithm on the previous slide, but the same problems persist, especially the learning rate tuning problem and this crude scaling by the maxima at a given feature. And if we compare it with the optimal SGD bound, still we don't get this type of quantity in which the units will cancel with each other for every term in the sum. Okay, so here is our solution. So our algorithm is based on recent work on unconstrained and adaptive online learning. So there was a sequence of papers which deal with the same problem we want to deal with, essentially to getting rid of hyperparameters of the algorithms. And the technique we are using here is essentially the technique developed in all these previous papers. And I'll try to explain what stays behind the design of our algorithm. So the idea is that we want to have the regret of the algorithm with respect to W star upper bounded by some quantity which is data dependent in general. So for example, for SGD with optimally tuned learning rates for each feature, this quantity would look like this. So this would be regret bound. As you can see, it depends on the W star vector, but it also depends on the gradients, and the gradients themselves depend on the feature vectors. So it's some kind of a quantity which depends on the data and the W star, and even possibly the weight produced by the algorithm in the previous iterations, plus some additional lower order term which we know how to deal with. Okay, so we are just going to put this regret bound. So F is the regret bound, which we are hoping to get. We're going to put it to the left-hand side. Okay, well, forgot that. First, we are going to get rid of this dependence on the data by just putting everything into the index, capital T. And then we are going to move it to the left side. And then we can think of the following. The goal of the algorithm is to minimize the so-called penalized regret. So there is additional function, ft, which is the regret bound. And this is a penalty for the W star, actually, not for the algorithm. So some W stars, they will have a larger penalty. The others will have a lower penalty. But the goal is to minimize this penalized regret by some factor which is essentially constant, or lower order term at least. Okay, so now we'll just we'll do the following. So this is a standard trick in online learning. So regret is the sum of losses of the algorithm minus the sum of losses of the optimal weight vector. So we can group them for each trial. We can group the losses by taking difference between the loss of the algorithm and loss of the best weight vector. So this is on the left side here. And now we can use the convexity of the loss and upper bound it by the gradient at WT. So this is the gradient observed by the algorithm, multiplied by the difference between WT and W star. So this, on the right-hand side, is the upper bound on the difference between the two losses. The advantage of that is now we have somewhat linearized the problem, because now we have essentially a linear function on the left-hand side. So I essentially use this trick to get an upper bound on the left-hand side, which is in terms of these products with gradients. Okay, so now I'm going just to use a different notation somehow. I'll just note that W star is the same in the sum, so I can take out W star outside and define the negative cumulative sum of the gradients by denoted by G sub t. I'll just plug in G sub t here. So this is what I want to minimize, right? And this inequality I want to maintain. And now I want this to hold for any W star. I don't know what W star is going to be. And I would like this to be true for all W stars. So if it's going to be true for no matter what W star is, I actually want to have this, right? So there are two quantities which depend on W star, this one and this one. And I want the left-hand side to be smaller equal than the constant, so I want the left-hand side to be smaller equal than the constant when I put a supremum over all W's on the left-hand side. And here we have a definition of some mathematical quantity. Maybe someone can recognize what it is? Yes, it's a dual. It's so-called Fenchel on convex conjugate of the function ft. So that's exactly the definition of Fenchel conjugate. So we can actually compute it for most of the functions. And this conjugate is defined, is usually denoted by f star. It's a conjugate of f. And this is a function of g, because w star is maximized out. So it's not really an argument anymore. What is left here is this gt. So it's a function of gt. So now we need to show this. Like the sum of this product between gradients and wt's plus this convex conjugate at the final cumulative gradient, negative cumulative gradient gt, is supposed to be bounded by a constant. But the good thing here is that we don't have w star anymore. We don't have the optimal weight vector anymore. It disappeared. It has been maximized out. It has been eliminated from this inequality. So we can just design the algorithm to keep the left-hand side small. And that's essentially how the algorithm is designed in our case. Actually, this property doesn't leave that much room to change the algorithm too much. So it's almost determined, the algorithm on the next slide, which are going to, it's almost determined by keeping this inequality tight. Okay, so what kind of function we are going to use? Well, we are heading for a regret bound, and I told you before that f is just the regret bound we want to get, and we know what kind of regret bound we want to get. We want to get optimal SGD bound. So, in fact, we are going to choose this penalty function, or the regret bound f, to be of this form. So it's a sum over coordinates, a function of a product between wi star and this square root of the sum of squared gradients. Let me call it just standard deviation of the gradients. It doesn't have, I mean, standard deviation should have a mean subtracted, but let's forget about that and let's just call it a standard deviation. And the function we are going to use is of the form x log x. So it's slightly it's decreasing slightly faster than a linear function. This is because if we only had the function f of x equal to x, then it would not be possible to get this type of bound in general. But having f of x being identity function here, so it would just be the sum of w star times sti, would exactly correspond to optimal SGD bound. So here we are going to lose a logarithmic factor. Yes?
I didn't understand one thing about getting rid
Okay, so we want to...
W star is the optimal weight vector.
Yes.
And later we use the supremum over W star.
So W star is actually any vector, in fact. If it holds for optimal, it's going to be for the other vectors usually. So the idea is that we just want this bound to hold no matter what W star is. So that's the idea. I'm just using the optimal weight vector all the time here to have some kind of an intuition what W star could be, like what kind of W star we are interested in interested in comparing with.
And the latest supremum will not be achieved by the optimal.
Well, not necessarily. But if it's but the optimal one is also going to satisfy this because it's going to be satisfied by the supremum, right? So in particular, the optimal one will also satisfy it. So in a sense, we can think of adding this f as some kind of not optimal one, but optimal regularized one. So this is like a regularization term of sort. Okay, sure. Where was it? Okay. So if we had an identity function, we would get the optimal SGD bound, but it's not possible to achieve that. One can show that this is not possible. So we need to have a function which is growing slightly faster than linear, and simply x log x is a good choice because logarithm grows very, very slowly. And by the way, the conjugate is then exponential. Okay, so how does the algorithm look like? The algorithm is called simply Scale-invariant online learning, and we found a good acronym, SCIOL. And I'll just show you the second version because the first version didn't work too well. But this one does. Okay, so what do we do here? We keep track of some data statistics as before, so nothing new. For instance, the maximum value at a given feature, and then we have sum of squared gradients. So this is like the squared standard deviation. And then we have a negative cumulative gradient. So the sum of gradients encountered in the past with a minus sign. And then there's one more variable, which we'll call a reward variable. It's a name from previous papers on this topic. And this reward variable starts with some value epsilon. It can be, say, 1. And then each time we add a negative product of the gradient and the weight vector, and this is how this reward variable grow. Okay. So this is how the weight vector looks like. It seems quite complicated, but maybe let's go through all this stuff. So first, there's this theta I, which is like a cumulative gradient divided by the standard deviation when there's additional max here. But it's not that important because this term s squared, it grows linearly, right? It's a sum, and max is a single number. So usually the second term is going to be dominated by this one, so you can forget about that in the interpretation. But anyway, it's dimensionless. This theta is dimensionless because we take a gradient, which has a unit, the same unit as a feature vector, and we divide by the so-called standard deviation, which also has the same unit as a feature vector. So it's like some kind of a normalized cumulative gradient, this theta. And now here, what's this thing here? It's essentially theta, except that if theta exceeds 1 or minus 1 in any direction, we cap it at 1. So if it's between minus 1 and 1, it's just identity. If it's outside this range, we cap it at either 1 or minus 1. And then we again divide by the standard deviation and multiply by this reward variable. And if we do this unit analysis, everything works out nicely. So this is unitless. Then here, the denominator is essentially has a unit xi. So the weight vector has a unit xi because the reward variable is also unitless because it consists of the products for which units disappear. And we can actually get a regret bound, which is almost like a regret bound of this optimally tuned stochastic gradient descent, except that there's this tilde over in the O notation. This means logarithmic factors are hidden from you, so that it looks nicer. And there is additional max here, but as I said, it doesn't really matter that much because this quantity here, it grows linearly in T, while this is just a single number. Okay. So as I said, it's essentially a bound which is optimal up to logarithmic terms. Okay, so let's look at the algorithm somewhat more closer. Let's try to interpret what the algorithm is actually doing and compare it with the previous algorithms. And I'll make some simplifications here. So here again, the statistics gathered by the algorithm. That's the definition of the weights of the algorithm. Here is the definition of this theta vector. And for simplicity, let's assume that these theta i's, they are within this -1 to 1 range, so they are not being capped. So they're not too large. And in case when they are not too large, so assuming that the numerator here is no more than the denominator, then we can just replace this whole quantity here with just theta I. But if we replace this quantity with theta I, and theta I contains the same expression as here, then we can actually rewrite it in this way. So we can rewrite our weight vector definition as this reward variable, or let's call it learning rate, multiplied by the cumulative gradient divided by the sum of squared gradients plus squared maximum. Okay, so that's a somewhat different expression than for stochastic gradient descent, because stochastic gradient descent is defined by quantifying what's the update from the previous weight vector. Here we don't have a previous weight vector. We always have like a closed form expression for the weight vector without referring to the previous one. But we can think about what's actually changing in the weight vector, and approximately we could write that the new weight vector is going to be the previous one minus the current reward variable or learning rate divided by s squared. I did some simplifications here for better interpretation. For example, I dropped this term here. And then the gradient, the cumulative gradient is going to be just replaced by the current gradient. So now it looks much more in the spirit of stochastic gradient descent, except that there is this scaling by the sum of squared gradients. And now we can compare it with SGD and ADA-grad. So SGD just updates the weight vector by subtracting the current gradient multiplied by the learning rate. ADA-grad does the same, but it scales inversely to square root of sum of squared gradients. And here we scale inversely to sum of squared gradients. So we do not take a square root. That's why the units are correct here. But of course, in this case, the denominator grows linearly in t in general, because this is a sum, right, of t terms. Here it's just a square root. And sometimes having effective learning rate, because that's we can think of effective learning rate, to be decreasing so fast, inversely proportional to t, might lead to two small steps after some time. So here we make the learning rate adaptive in a sense. The learning rate can grow itself. And what's the interpretation of this learning rate update here? So you can think of change in the learning rate to depend on the relative alignment of the current weight vector and the gradient. So if the current weight vector is aligned along the negative gradient, it means that we are predicting in the, let's say, right direction. And then this makes the learning rate to increase. Otherwise, the learning rate can decrease, right? So the learning rate is also non-monotonic here. Okay, so for the remaining part of the talk, I'm going just to show you how does the algorithm work. So first, I will show you a simple, let's say, illustrative example on artificial data. And then I'll just show you some preliminary experimental results. And yeah, then I will conclude. So the experimental setup here for this artificial data experiment is that we take a feature vector, which is from R to the 21, so it's 21 features, and why 21? Because the feature scales are from 2 to the minus 10 to 2 to the 10, right? There are 21 of them. So we assume that each feature is drawn from a normal distribution with 0 mean and a standard deviation sigma I, which is between 2 to the minus 10 and 2 to the 10. So these sigma i's are natural scales, right, on each feature. And this is not some intricate example, because this is essentially 1/1000, and this is 1000. So there's a million relative ratio between the largest and smallest scale of order of 1 million, and that's I think that can be typical in some fields to have this type of magnitude between scales. And then, given a feature vector drawn from the normal distribution, we draw a label. So it's a binary classification experiment. We draw a label from a Bernoulli distribution with parameter p of x, where p is just a sigmoid. So it's like a logistic regression model. So p is a sigmoid transformation of the dot product between the feature vector and some hidden w star. So w star is like a true weight vector, which is hidden. And w star has values on each feature, which counterbalance the feature scales, so that every term in this product is of the same order, of order 1. So the values of w star are inversely proportional to standard deviations. And then we just train linear models with logistic loss. Logistic loss seems appropriate here because actually this is the true model behind the data, logistic regression. And then we run algorithm on a sequence of 5,000 examples, tested on 100,000 examples, and then we repeat it many times just to have a more stable result. And there are several algorithms which we tested, so that's SGD. So SGD, we chose the learning rate scheme to be decreasing as 1 over square root of t. This is actually suggested by theory, and this is also often done in practice. Then we also use AdaGrad and Adam, and these two algorithms which I mentioned during the talk, normalized adaptive gradient and the scale-free mirror descent. And two algorithms from this work. I only showed you one version number 2. There was also version number 1. You will see in a moment why I didn't show that one. And well, these algorithms which I presented from this work, they don't need learning rate because they don't have hyperparameters, but all the others algorithms, they have at least one hyperparameter, sometimes more, the learning rate. And according to this quotation at the second slide, we actually tuned the learning rate. And we just set it to one of the values from this range. So that's like a exponential grid of values from 0.001 to 10. And we just choose the learning rate. Well, we actually plot all the learning rates here in this experiment. So these are plots. So before I'll tell you more about the results, let's look at what are these two lines here. So that's a number of iterations or number of examples seen in the online learning process. And here's the cross entropy on a logarithmic scale. And this bottom dashed line is the minimum achievable loss in this problem. So since we have a full control over data generation process, we can actually compute what's the so-called base risk. So the loss of the optimal weight vector. So no algorithm can actually get anything better than that. Funny thing is that the other dashed line is the loss achievable by the algorithm which always plays with 0 vector. So it doesn't learn at all. So everything which is above this line is just some nonsense. I mean, it just means that the algorithm diverged. And it actually applies to most of the algorithms. So let's look at what's happening here in this small range. So it's just a zoom, right? To this small range of values. And as you can see, there are a lot of curves here because each curve corresponds to a single algorithm with a single learning rate. Since I told you that I think there were like 11 or 10 possible values of learning rates which we tested, for every algorithm there are 10 curves of different colors. So as you can see, the curves which are here on this plot are mostly curves associated with algorithms which are scale invariant. So this NAG and SFMD, so that's this normalized adaptive gradient and scale-free mirror descent. So these two algorithms that I mentioned above. And well, there is some, there's AdaGrad here with particular learning rates, which is still better than a trivial solution. I think SGD is not present here at all. And there are two algorithms, the scale-invariant online learning algorithm which we developed. That's the version number 1, which are clearly too conservative. And that's the version that I presented to you. So as you can see, this blue version, our algorithm doesn't get the optimal the optimal loss here in this experiment, it doesn't have any learning rate to tune. So without tuning the learning rate, we can get almost to the minimum among all these algorithms which we compare to. Okay, so that's the artificial data experiment, and I still have 4 minutes at least, right? So I'm going to show you the real data experiment on several simple data sets from, I think they're from UCI, maybe except MNIST, of various size, which is pretty small for current standards. So we just took logistic regression. By the way, everything here generalizes to more than 2 classes very easily, in the same way as log loss generalizes to cross-entropy loss for multi-class classification problems. So we also chose logistic regression, trained using the cross-entropy minimization, and for each data set and each learning rate, we run the algorithm 10 times. And for all the algorithms which have varying learning rates, we only choose the best learning rate. And we only show the best learning rate. So the learning rate which resulted in the smallest test error, right? So in a sense, it is biased towards these algorithms. There are several algorithms here. One which I didn't talk about is also a version of one of these algorithms which are adaptive from the past. It's not scale-invariant, but it's an adaptive algorithm, so it doesn't require a learning rate. And our algorithms here. Okay, so for example, for MNIST, there's not that much to be seen. Okay, so maybe just pay attention to this light blue line is somewhere here. So here is not that much to be seen. Everyone except these two works well, so that's why I didn't mention the first algorithm. That's another experiment on the bank data set. So as you can see, our algorithm somehow works better than the others, or at least it's competitive among the best. Here's another example, a similar situation for census. A good thing about our algorithm is that, okay, so what are these shades here? These are, let's say, standard deviations, because everything was repeated several times, so we can compute the standard deviation of the results. So these shades, they denote standard deviation. So as you can see, our algorithms are actually quite stable. They don't really have this shade around, because it means that they essentially perform in a very similar fashion in different runs. A similar story with cover type, except that the other algorithm, this COCOP, seems to be somewhat better. Here, not that much to be seen again. And okay, there's nice plot. You can see this nice blue curve below, and so on. Okay, I think I'll just convince you at least that this somewhat works, right? Without tuning the learning rate. So okay, so our contribution here is in algorithms that are adaptive in the sense that they do not require to tune the learning rate, and at least in theory, in terms of the bound that is achievable, they can get essentially the same guarantees as stochastic gradient descent with learning rate separate per each coordinate or per each feature vector, tuned optimally to optimize the actual bound. And for future work, we would like to have algorithms which not only works for linear models, but also work for deep models. So first of all, in deep models, you can think of deep models as stacking linear models in subsequent layers. And then we can think of features as activation values entering a given layer from the previous layers. Here we need to adjust the algorithm for mini batches, because mini batches are usually used are used in deep learning to train the networks. And also we want to compare the behavior of our algorithm with using a batch norm layer, right? So batch norm is somehow apparently being used for the somewhat same reasons as the scaling in our algorithms. So to avoid these scaling issues in the weight vectors or different scales. So at least in the first layer, we can somehow take into account the differences in scales by simply normalizing the whole data set at the beginning. But then we don't really have controls over the scales in internal layers. So maybe batch norm is somewhat some sort of a solution to this problem. And we want to see how does our algorithm compare with batch norm for deep models. So I think that's all. Here are just references. And yeah, that's all I have to say. Thank you.